This segment will cover the nephron, and this is really where we turn plasma into urine. It's going to take all the fluid that was filtered by the glomerulus and determine what needs to stay and what goes. So in the nephron, there is going to be significant movement of electrolytes, water, and other substances across the epithelial cell in order to reclaim or remove products from the blood. Now, there are three main ways that they can do this transportation. The first is an actual transporter, whether it requires ATP or not. And on the next few slides, you're actually going to see these symbols indicating these types of transporters. The second way that you can do it is diffusing a substance through their own appropriate channel. And finally, there's osmotic diffusion, which is actually based on an osmolar gradient, where water is going to travel from more concentrated areas to more dilute areas. So we've seen this slide before in the introduction lecture, but remember that osmolality or osmoles are determined by the number of particles, not the weight. Once again, sodium and urea are going to be your primary osmoles that are excreted in the urine. And I want you to know that the kidney is always trying to equilibrate the osmoles so that everything is equally diluted. So the proximal tubule is our first segment of the nephron, and it's going to be responsible for the large majority of the reabsorption inside of the nephron. Now, 100% of glucose and amino acids are absorbed in the proximal tubule. And additionally, there's almost 70% of several electrolytes that are recovered from the urine and returned to the blood. Bicarbonate is one of the most important substances that is reclaimed and created here because it's responsible for that pH maintenance that we talked about in the acid-base physiology lecture. Now, if we're losing all of that in the urine, we become acidotic very quickly. Finally, sodium and water are actually removed from the urine and they're put into blood at equivalent rates in this area, so the overall osmolality in the lumen won't change. But it's important that we get all of these substances back into the blood while removing those that are unnecessary. Now, I want you to notice that every single portion of the nephron is going to have an active sodium-potassium ATPase pump. So over here is where your blood and interstitium is in the red. The orange is going to be your epithelial cell that's lining the tubule lumen, which is over here in the yellow for urine formation. So I'm going to show you a bunch of transporters, and it's going to get really confusing and large and upsetting, but I'm not trying to have you memorize every single one of these. The only reason that I put them on there is because your instructor did, and I want to make sure that you can follow where all of those electrolytes are going. However, there are some very important things in each segment that we need to talk about. So, what this sodium-potassium ATPase pump does is it allows for active transport against a gradient. Now, that means that it creates a low charge inside of the cell because it's actively pumping out sodium at the same time as exchanging for potassium. And so that actually creates this negative environment in here, encouraging more electrolytes to travel from over here in that filtered substance all the way back into the blood. The next thing that's recovered is actually bicarbonate, and it starts as carbonic acid inside of the cell and then dissociates into bicarbonate that's reclaimed in the blood and hydrogen ions, or in other words, that acidity that's released into the urine. And we'll talk about this a little bit more in depth in the next slide. But like we mentioned, there's actually going to be a lot of glucose, amino acids, and even phosphate ions that are recovered in this area. So let's talk a little bit about that bicarbonate. Now, it's freely filtered by the glomerulus. And remember, anytime we say it's freely filtered, that means that if we don't get it back, then it's lost in the urine. It's just pushed straight out of the body. So the way that there's two things that are done here that are extremely important. The first is that we create bicarbonate because some of it's being consumed inside of the blood. And that's an issue because if we only reclaim what is lost in the urine, then we're still at a deficit because some of it was consumed. So we start by having CO2 and water that are easily diffusible into the cell. They combine with carbonic anhydrase, which is an enzyme, to create carbonic acid. That then breaks apart and dissociates into the bicarbonate and hydrogen ions that we talked about on the last slide. So that's the creation of bicarbonate. But from there, we're actually going to also recover the bicarbonate that was lost into the urine. And it can combine with that hydrogen ion, and it essentially does the reverse of what we just talked about. It creates carbonic acid and then dissociates down with carbonic anhydrase into CO2 and water so that it can come back through the cell. Now, this may seem like, well, we're just making what we just tried to get rid of in terms of the hydrogen ion, but remember that this allows us to absorb sodium. It allows us to absorb that bicarbonate, and so we have other chances to get rid of the hydrogen ions later. So a few things: we're going to reabsorb, we're going to generate, and we may even secrete a few hydrogen ions. So this is a summary of, from beginning to end, where those electrolytes are going. Now, I usually put this straight line across, even though I know that these receptors aren't really linked, but it just helps me to see, hey, glucose is going all the way through, sodium is going all the way through, potassium is going in, and then later it may even go out. So that was all the early proximal tubule, and now we're going to look at the late proximal tubule, which has some other responsibilities. And now remember that high concentration of K that's in here from the ATP pump? Well, it's going to pump out by helping us recover chloride ions. That process can only happen if that ATP pump works, so we can recover chloride all the way from the urine. Additionally, we're going to get rid of some anions. The main anion I want you to think about is formate, and it's going to combine with those hydrogen ions that we just secreted and diffuse back into the cell. Now, that doesn't make a lot of sense. Once again, we're just kind of going in a circle. It cancels out the formate we just got rid of and those hydrogen ions, but remember that we have to recover this chloride. So in order for the pumps to work, that's what we need to do. So here's a full summary of what just happened in the proximal tubule, and this is the most difficult of all the tubules. It only gets easier from here. Now, I want to touch for just a second on hyperchloremia, because this occurs in certain types of metabolic acidosis. Now, if bicarbonate is consumed and it's gone, then we aren't able to let this potassium bicarbonate pump function, but we still need to get, sodium bicarbonate pump. But we still need to get sodium through. We still need to reabsorb that sodium, and so chloride can actually compete with this bicarbonate in order to be reabsorbed in the blood, for this sodium to be reabsorbed. As a result, then our chloride levels continue to increase, which gives us the hyperchloremic metabolic acidosis. Now, the descending limb is the second portion, and it's going to be your favorite because the only thing that's absorbed here is water, and it's passively through their own little channels. So we just removed a bunch of solutes from the urine above in our proximal tubule, right? Now we want to concentrate that urine by pulling out as much water as possible so that we don't lose it. So we're going from our light urine to our dark concentrated urine. Now for the ascending limb, there's both active and passive in the thick and thin. We're going to talk mostly about the active thick section and all these different electrolytes that are reabsorbed, but know that this is impermeable to water. And that's super important because it allows us to create a gradient. So here's what we're paying attention to. Once again, everything has a sodium-potassium ATPase pump. However, this is the most critical pump that occurs on the ascending limb. It's a triple pump. It's got sodium, potassium, and 2-chloride. However, ammonium can actually also compete with potassium to travel onto this triple transporter. Magnesium and calcium are absorbed in this area as well. This tells you where all the electrolytes end up. And there's a lot of potassium going in and out of here, but I want you to focus mainly on this triple pump. For the distal convoluted tubule, here we're reabsorbing some of those same ions, but we're also reabsorbing bicarbonate. It's not nearly as much as in the proximal tubule, but we still don't want any to escape in the urine, so we have to do it in most of the segments of the nephron. We're also trying to excrete protons and potassium if we have too much. So here you're starting with this sodium chloride pump, a sodium potassium pump, and then calcium that's being reabsorbed along with that sodium. Here's where those electrolytes end up. Finally is the collecting duct, and this one is also a little bit complicated, but what our purpose is here is to reabsorb the final water that's left in there and to allow for excretion of those acids and any products that we don't want, extra potassium, so forth. So we do that through two different hormones. The first is aldosterone, and it's a mineralocorticoid, which is a steroid created in the adrenal cortex. The purpose is to increase sodium and water reabsorption because sodium and water are going to follow one another. So if we absorb more sodium or if we absorb more water, then we're going to be able to increase the blood volume and, more importantly, the effective circulating volume, which is the volume inside the vessels. Additionally, we want to get rid of any of that excess potassium and hydrogen ions, so aldosterone helps facilitate acid secretion as well. And there are multiple enzymes or states in which this is stimulated. So high potassium will allow us to release more potassium. Angiotensin 2 will allow for aldosterone recovery in order to increase the circulating volume, and ACTH, which is from the brain. The next hormone is antidiuretic hormone, and it's in the name antidiuretic. So when we have too much water leaving in the urine, we want to reabsorb it. So in the presence of ADH, also known as vasopressin, then we can increase blood volume. Now this is stimulated when there's low blood volume or highly concentrated, or in other words, high osmolality in the blood. It says, let's dilute that with some more water. So here's how this happens. So there's a special sodium channel here called ENaC, or the epithelial sodium channel. Now it allows for sodium to be absorbed without a pump system. Additionally, in order to balance those charges, potassium is sent out into the lumen. Now, the more sodium that's delivered here, the more sodium that's delivered to the blood and the more potassium that is excreted. From there, we talked about how the beginning of the nephron is permeable to water. The middle is impermeable, that's that ascending limb. And over here in the collecting duct, it can be variable. In the presence of ADH, it's permeable. Without ADH, it's not permeable. So what we do is ADH comes over and attaches to its receptors. And it's a V2 receptor because it's vasopressin, V1, 2, or 3 receptors. And they insert what are called aquaporins, which are specialized water channels that allow for a massive amount of water to be reabsorbed. So that water continues to reabsorb so that we can concentrate that urine. So think high ADH means high water absorption and a more concentrated urine because the water's now back in the blood. Now in the second type of cell in the collecting duct called the intercalated cell, we just spoke about the principal cell, more bicarbonate reabsorption is happening. Like we said, we want to absorb every single portion. And we also are pumping out some hydrogen ions. The reason is because, The reason is because we're going to bind this hydrogen up to other substances in order to remove them from the body. So I want you to pay attention to where aldosterone is acting. This is the ENaC channel, the sodium potassium ATPase pump, and the hydrogen pump. So I've removed everything else so you can see it clearly. That's our second hormone that allows for more sodium and water reabsorption. So now we end up with all of these hydrogen ions in the urine, and we don't want highly acidic urine. And we have other things that we still need to get rid of, including our ammonium and titratable acids. So ammonia comes in and binds up with a hydrogen and gets excreted as ammonium. Now that's created when amino acids are synthesized, so we have to get rid of it out of the body. The same thing occurs with other titratable acids. Now, phosphate kind of varies with dietary intake, and between phosphate and ammonium, we can only really secrete a third of our acids. And so we really need that bicarbonate to be able to consume the other 2/3. Notice aldosterone and ADH and where they act. And notice that we're getting rid of a lot of those hydrogen ions. Finally, let's address the reason that we care about all of these crazy ions that are moving back and forth. I want you to know that the primary way that you're going to get tested on your understanding of what we just talked about is through diuretics. This is the clinically applicable reason why you need to understand any of that electrolyte movement. And here's one summary page of all the different places that those electrolytes act and what they act on. Here's another summary page, but I'm going to go through each section specifically. So the first is carbonic anhydrase inhibitors. And where they act is on that conversion of CO2 and water to carbonic acid. And they block that from occurring. Now that stops sodium from being reabsorbed and allows it to exit out of the body. This is used only in very few instances. There are no diuretics that we focus on that work in the descending limb. The next is the ascending limb, and these are loop diuretics that act on the triple transporter. In the distal convoluted tubule, we have thiazide diuretics, which are actually blocking the sodium chloride. These are thiazide diuretics. And finally, in the collecting duct, we have multiple types. The aldosterone receptor antagonists, so everywhere where aldosterone works, the receptor antagonists are going to block. This is spironolactone and many of our potassium-saving diuretics, because if it blocks here, then potassium isn't removed from the body. And finally, the ENaC blockers, which are used to block the sodium channel and allow for more sodium and water to escape, because we said that the more sodium is reabsorbed, the more water is reabsorbed. And those are your diuretics. Make sure you pay attention to those, because that's primarily, especially on the pants, how you're going to get tested.